Hello everyone, here's a new application of the 9-point circle, and let's have a look at the statement of the problem. Triangle ABC has orthocenter H and 9-point center N, and let L be a line through that center, 9-point center, perpendicular to the line segment AN. And let the feet of the perpendiculars from B, C, and H to that line L be X, Y, and Z. We need to prove that AN plus HZ is equal to BX plus CY. What I would recommend at this point is that you go ahead and pause the video, draw a sketch, try to see if you can find some relevant points, or some ideas that you can use to prove the statement of the problem, and then you can come back in. So there you are. I still have the statement of the problem, so that's what we really want to prove. So let's go ahead and mark some of the points given in this shape. So our triangle is ABC and the vertices are clearly marked as blue. So H, this point, is the orthocenter, and N is the, as you can see, 9-point center. So a couple of remarks are in order. So first of all, I would like to kind of remind you that the 9-point circle will bisect any line segment from point the orthocenter to the vertices at such. So K, that point, so HK is actually equal to KA. In a similar way, H, this point, is equal to this point to B. So that distance is equal to, and in a similar way you can see that, so that point would be the midpoint of HC. But so very important point, K is actually the midpoint of AH. So let me write that down. AK is equal to KH. So that was my first observation. But once you make the observation, we know from a previous video that this point is diametrically opposite on the 9-point circle to the midpoint of the opposite line segment. So that's very important. L is the foot of the median from point A, or you can call it the midpoint of BC, and as such, the green line is a diameter. On one side you have the midpoint of the side, and on the other side of that diameter you have the midpoint of that line segment AH. So that's crucial for the proof. So I hope you can make sense of this result. You can refer to our previous videos, particularly the proof and the existence of the 9-point circle. Both the first and second proof videos are very useful to establish this result. So now I did go ahead and draw the 9-point circle here, and moreover we have this line mentioned in the question, line L, I believe. So this line is called line L, and on that line we further mark 3 other points. So first of all, line L is defined to be perpendicular to the line segment AN. All we did is draw the line segment AN. I already know the location of N, and you can easily draw the perpendicular line here, and then you go ahead and start dropping perpendiculars from point B, from point C here, and from point H. So that tiny right angle here. So all these newly defined points, X, Y, and Z, are the foot of those projections, if you will, from the points B, H, C to our line. But then we have quite a few parallel lines. First of all, those red lines here are definitely parallel to each other for sure. But then there's even more, because we established the very definition of the line L was that it was perpendicular to the line segment AN. As such, AN is also parallel to these 3 lines. So therefore, let's write that down. So we can say that line XB is parallel to line, let's call it HZ here, which is further parallel to line YC, and finally which is parallel to line AN, or line segment AN, if you will. Okay, that's fine. But now let's make it clear. L was the midpoint of line segment BC, so let's write that down. So that was the first result, second result, and now it's the third result here. So BL is equal to LC. But that's very important for us because now I have a trapezoid here, and actually I have a right trapezoid here. XYCB is a trapezoid, so because XB is parallel to YC. And furthermore, what I will do is I will drop an altitude from point L to our line L, from point L to line L, so that's funny, but there you go, and that's 90 degrees. Let's call that point, I know it's kind of the location is kind of vague, but let's call it L prime. So now can you see that because L is the midpoint of line segment BC, it must be that L prime is the midpoint of line segment XY. You can just think of this trapezoid here, and then you have in a sense this midline of the trapezoid. So if one side is equal, the other side must also be equal here, and that's exactly what we're claiming. So therefore this implies that XL prime is actually equal to L prime Y. But if that's the case, we know from the property of the parallelogram that if we call this A and C, that midline has length A plus C over 2. In that case, our midline is LL prime, and it immediately tells that 2LL prime is simply equal to XB plus YC. So, and that's wonderful. So now I can rewrite the right hand side here as 2LL prime. Now let's do a similar trick on the other side as well. So what I will do again, I will drop an altitude from point K to our line segment, so it's gonna be so something like that, and let's call that point here, oops, let me use my pencil here, so that point right here, so that tiny bit point between Z and N, let's call that point K prime because it's the projection of point K onto the line L. And now again we have a similar picture. HZNA is a trapezoid, and we know HA, the midpoint is K. It must be that K prime is the midpoint of ZN. So you can say result 4 ZK prime is actually equal to K prime N. But then again, by the same reasoning, because KK prime now is a midline of our trapezoid HANZ, it must be that KK prime is half of the sum HZ plus AN. So that sum here is actually equal to 2 times KK prime. KK prime. Now all we need to do now is to establish that KK prime is actually equal to LL prime. That completes our proof. And why is that the case? Because you have two similar triangles here. Remember what we said early on. The line segment KL goes through the midpoint, through the 9-point center here. And as such, you have two perpendicular lines to the line L. It must be that KK prime is parallel to LL prime. And so we have angle similarity here. In fact, more than similarity, we have a congruence here because Kn is equal to NL. Kn is equal to NL, and then you have a bunch of equal angles here and here. For instance, angle K prime Kn is equal to angle NLL prime. It must be that, and so let me write down as the final result here, result 5, triangle K and K prime is congruent to triangle L and L prime. And that basically established that desired result that K prime is actually equal to L prime. And that solves our problem. So please make sure to review this solution again, if you will, and construct your own picture. I usually construct my pictures on GeoGebra. It gives me a lot of intuition on solving some hard geometry problems. Hope you enjoyed the video. See you in our next problem set.